Hello and welcome back to the November 2025 TZ3 Chemistry IB Exam walkthrough. We're just going to keep going out through this HL exam, going through number questions 21 through 25. So looking at this question number 21, this is talking about biofuels instead of fossil fuels and their disadvantages. And so honestly, the biggest ones that you want to look for this are: one, is it true? And two, is it a disadvantage? So this first one, land is used that could be used to grow food. That is very much so a disadvantage. We are losing land. People are losing food. That is bad. So tentatively, we're going to say A could be right, but we're going to look at the other ones first. B, combustion releases more energy per mole of fuel. There's two things wrong with this. One, if it was true, that would be an advantage because combustion, like biofuels, ethanol is one of them. Ethanol undergoes combustion. So that would be releasing more energy. That would be an advantage, not a disadvantage. Secondly, releases more energy compared to what? Because like biofuels definitely don't release the most energy out of all of the fuels overall. But like if you were comparing it to something specific, then maybe that could be true. But either way, it's not, we don't know if it's true based on the details that were given. And two, it would be an advantage if it was true. C, emissions of carbon dioxide to the atmosphere are lower overall. We want less emissions. So once again, that would be an advantage, not a disadvantage. D, crop waste can be used as fuel. Once again, that is using things that would have been wasted otherwise, so that would be an advantage, not a disadvantage. And so this one would be A. Okay, and so now looking at this number 22, we have which products may form when propane undergoes incomplete combustion. And so it's important to remember that whenever we have incomplete combustion, that essentially means we have not enough oxygen. Okay, and so normally with combustion, like complete combustion, is we have some sort of, I'm just going to put species X, reacting with oxygen, and we form carbon dioxide as well as water. Okay, and so whenever we have not enough oxygen, is that essentially is going to affect the amount of CO2 that is formed. And so we are going to produce CO2 as normal, but we also might produce some CO, less oxygen, or maybe even some C, which has no oxygen and is just soot, plain old carbon. Okay, and so for that reason, this one's going to be D. And so you also may ask, and you should ignore my cat in the background if you can hear her, but you may be asking yourself, but Mr. Majors, D doesn't have water in it. Here's where you got to look at the wording. Is the only option that has only in it is A. Otherwise, all of these options leave room for essentially saying water is also produced in addition to it. It's just not saying it explicitly. It's like A is carbon dioxide and hydrogen gas only, but these other ones are carbon monoxide, carbon, hydrogen gas, so on and so forth. But they don't say only, and so therefore it's still valid. It's okay. Moving on to this number 23, we have a crystal of copper 2 sulfate is in equilibrium with a copper 2 sulfate solution. So we essentially have an equilibrium between the solid and the aqueous forms. And so we have this equilibrium that's happening in a stoppered flask, which essentially just means that it is closed and it is at a constant temperature. And it's asking about what observations are possible. And so we're going to kind of go through each of these and see whether it's possible or not. So first one is the color of the solution becomes darker. And so the biggest thing to realize here is that this is at equilibrium, okay, which essentially means the rate of the forward reaction is going to be equal to the rate of the reverse, okay? And so if the color of the solution was becoming darker, that would essentially mean that the rate of the dissolution is going to be faster than the rate of the crystallization, which because it's equilibrium, those rates should be the same. So that should not be possible. Meanwhile, with B, the volume of the liquid decreases. That literally doesn't make any sense really anyways, because it's in a stoppered flask at constant temperature. This is a closed system. Nothing should be leaving the system. So B is not possible. Meanwhile, C, the shape of the crystal changes slowly over time. And then D, the size of the crystal decreases. So D we're going to look at first because it's more obvious. So D, the size of the crystal decreases. That would be essentially the opposite of A, where that's essentially saying that the rate, not even like the opposite, that would actually just be the same as A. We're basically saying that the rate of the dissolution of the solid is going to be faster than the rate of the crystallization. But once again, this is equilibrium, so that is not the case. And so C, it is right based on process of elimination, but it's also right based on conceptual reasons. And so the shape of the crystal changes slowly over time. And so this essentially is based on the fact that this is a dynamic equilibrium. Okay, and so that essentially means that because the rates is you essentially have happening at the same time as in this flask, I'm going to boop, boop, boop. In this flask is you have some solid that is dissolving into the solution, and you also have some solution that is crystallizing back onto the solid. This is happening at the same time. And so if you were just looking at it, you wouldn't really be able to see anything happening because this is a dynamic equilibrium. It's happening pretty much simultaneously at the same time. Okay. However, the crystal, the size wouldn't change, but because there's no change in the mass, because it's still the same rate is happening, but because it's still happening, like if you zoomed in on it, you would be able to see that, like, as a crystal dissolved and then precipitated back on and dissolved and precipitated back on and dissolved and precipitated back on, that would change the shape of the crystal. It would not change the size of the crystal because that rate is equal to each other. But because it is still changing on the microscale level, that would still change the shape of the crystal very slowly over time. Okay, and so for that reason, C is going to be correct for that number 23. Moving on to this number 24, we have a theoretical yield problem, which is great. And it's based on the reaction of we have a starting amount of ammonium carbonate and we have excess ethanoic acid. This is good because that means we don't have to calculate the limiting reagent. Yay! And so we have our ammonium carbonate, which is this guy right here. And so we're asking for our grams of ethanamide, which is this CH3CONH2. And then so it's careful to notice that this is essentially going to be based off of, first you're going to have to calculate, this is what we're looking for here. So first you're going to have to go from moles of this guy, our ammonium carbonate, to our intermediate here in this reaction. And then you're going to have to go to your moles of product. Okay. And this is also, you can tell that just based on the fact that you have two balanced equations, that means you're probably going to have to use both of them. That's crazy, right? And so we're just going to use dimensional analysis for this. So we have 4 grams. Nope, that's a highlighter. Boop, boop. We have 4 grams. Let's zoom in here. Of this, I don't want to write ammonium carbonate the whole time, so I'm just going to put AC. Why not? And so we're going to convert that to moles so that we can use our balanced equation ratio. And so we have the molecular mass right here that is in grams per mole. So we're going to divide by that to cancel out our grams. So we have 96.11 grams AC in 1 mole of AC, our ammonium carbonate. And so now we're going to need to go from moles of ammonium carbonate to our moles of this CH3COONH4. I'm too lazy to name that. And so we're just going to call that intermediate I. And so in our balanced equation, we have 1 mole of our ammonium carbonate. So that's going to go on the bottom to cancel that out. 1 mole ammonium carbonate. And then we are going to have 2 moles of our intermediate. 2 moles of our intermediate. And so then we can actually immediately go to our second equation. We can convert that now to our moles of our final product in a 1-to-1 ratio. So I'm just still going to write that down so that our units can cancel out because it's good practice. So we have 1 mole of intermediate forming 1 mole of product. And then finally, we can go from moles of product to our grams of product by multiplying by our molecular mass. And so we have this 59.08 grams of our product and 1 mole of product. And so before we even put this in our calculator, we can make sure that our units cancel out. This is why I always write them. It's important. So I'm going to go in red here. So we have grams of AC, moles of AC, moles of I, moles of P, getting our grams of P as our final product. And so now we're going to put this in our calculator. So it's going to be, I have my phone because I can't do math in my head, 4 divided by 96.11 times 2 times 59.08. And that is going to give us 4.92, which is going to be C as our final answer here for that number 24. And so now, moving on to this question number 25, we have this volume of ethyne reacting with hydrogen, and it's shown to be forming this ethane product. And so it's asking about this graph of what it should look like for the changes in volume over time, although also in the graph, it also has the changes in this ethyne over time. So I don't really know why it says hydrogen, because it's showing both. Anyways, and so the way that this kind of works is this is based on, honestly, just kinetics. There's no real, skill here, if you will. It's just kind of based on how reactions work. So both of these things that are in our graph, this C2H2, this H2, they are both reactants. And so whenever you have a reaction happening, your reactants are going to decrease as they are used up to form your products, which will be increasing. Okay, and so since your stuff is in, your reactants are in volumes, they're going to decrease in volume over time as the volume of the products increase. And so immediately that takes out both A and B, because in A, you have your volume of hydrogen somehow increasing. We're not miraculously producing more hydrogen, and this is not an equilibrium system. Meanwhile, with B, you have your hydrogen staying stagnant, and that really would not work either. Because you have to use some of it. And so in this case, we're in between C and D. And so this is where we have to think about limiting reagents. So we don't have any starting volumes, any ending volumes, whatever, but we do have the stoichiometry. Okay, and so we have that 1 mole of our ethyne produces 1 mole of product. Meanwhile, for our hydrogen, we have 2 moles of hydrogen produces 1 mole of product. And so if we were to do any stoichiometry with these starting materials and we were trying to find like the limiting reagent, we would have to essentially, to get moles of our ethane, our product, from however many moles of hydrogen we were starting with, we would have to divide it by 2. Meanwhile, if we had to do the same thing with this ethyne, it would be a 1-to-1 ratio, which essentially means that our hydrogen is going to be our limiting reagent. And I can even demonstrate this with fake numbers, which I'm going to do because I feel like it's kind of hard to understand in words. Like, I'm making up numbers here, by the way. It literally does not matter. Like, let's say we had 20 decimeters cubed. Actually, not even 20. Let's just say we had 2 moles of both of these, okay, as our starting materials. We had equal amounts of both. We had 2 moles of both, okay? And so if you have 2 moles of your ethyne, then because it's in a 1-to-1 ratio, that would produce 2 moles of product. Meanwhile, if you had 2 moles of hydrogen, because you have in your balanced equation A2H2 forming 1 mole of product, that would form 1 mole of product. Hence why your H2 is going to be limiting. And so with C and D, both of them, they are decreasing the amount of volume before eventually plateauing out. That plateau is because you're running out of material. Okay? And so in terms of which one is which, the only difference between these two is that in one of them, your ethyne is running out at a slower rate. Meanwhile, with the other one, your hydrogen is running out at a slower rate. And so the difference here is that because your hydrogen is going to be your limiting reagent, you are going to have that one that is decreasing at a more rapid rate. Okay, it's going to run out first. So you're going to run out of your H2 first, and you're going to have less of it there. Meanwhile, you will have still some ethyne left, therefore leading to D being the answer here. C would be the answer if you were running out of your ethyne first. But with D, you're running out of hydrogen first. That is why it is there, and it has a steeper slope compared to the ethyne. And so D is your answer for this one.